going to be streaming the contents of my screen and my voice onto the YouTube. So if you've ever sat in a stats class and thought to yourself, you know, I would have that if she could just say it one more time, you know what, you can hear it as many times as you want. The videos will live on in perpetuity on my YouTube channel, and I will put a link to all of those here once we're all done. Also, if there's more topics that I can help you with, if you ask questions and I say, well, I'm not going to talk about that today, but I talk about it elsewhere, I also wanted to point out that I keep all of my teaching materials online as well. So if you go to my course materials page next to it, you will see the full 2-semester version of my longitudinal and multi-level modeling classes. So I have a lot more material there, particularly more introductory material in the first semester, and then more general types of MLM material in the second semester. I also teach courses in structural equation modeling, and so all of that stuff is also available for you as additional resources. And I'm happy to point you towards specific examples or lectures if there's anything that we talk about that I think might benefit you. As you can tell, I like to keep things casual. We're here for 2 days. And I am well aware of the limits of the human mind, that you cannot absorb everything for 8 hours straight without adequate breaks. And maybe not even then, right? The human mind is not meant to sit still for this long. So I'm not going to talk for more than an hour and a half without letting you out to go thaw out of the room, go get more coffee or whatnot. So I have the schedule here. We'll try to stick to 20-minute breaks in the morning and the afternoon, and I'm anticipating over an hour for lunch. Is that going to be, let's see, where'd Brian go? Is that going to be, that's it. Okay. Okay, so yeah. That being said, if you need to step out for any reason, please feel free. You're not held captive in here. I also want people to feel free to ask questions. So one of the things that I was fortunate to do when I was a postdoc at Penn State was to audit some classes. And I was the person with my hand in the air about every 30 seconds because I was furiously trying to put the material together, the things that I had tried to teach myself somewhat successfully, mostly unsuccessfully, that I had someone in front of me willing to answer questions. I was going to be that person with my hand in the air to get it. So please, feel free to be that person as well. Ask as many questions as you feel like. I especially like questions about how does this apply to the study that I'm currently working on, or what I thought I heard you say is this, or how does this relate to this other thing that I may have read about. Please feel free to make this as interactive as possible. I know it can be intimidating in a large room to be willing to talk, but it does help when other people can hear and benefit from the things that you're saying as well. I have a suggested reading list as well as the stuff from the book. The book itself, let me find the page here. I wanted to also point out I've added something new to it recently. So yes, here's the book that I wrote. I was teaching longitudinal models for a couple of years and becoming increasingly dissatisfied with the texts that were out there. They were either too technical or they stopped too short in terms of dealing with the complexity of longitudinal data that's unique relative to just straight up multi-level modeling. And so rather than continue to complain about it, I wrote a book. This was 5 years of my life. So I would encourage you to read it. If your library probably has a copy, there's also e-versions that are for sale if you're one of those electronic folks. But more than that, I spent the year while the book was being published building this website. There are 4 different programs represented, and I have every single analysis mentioned in the book on this page. Example syntax, data, and output for everything, as well as an additional column here for spreadsheets that did calculations like pseudo R-squares or likelihood ratio tests. I am not an R user. I refuse to drink that Kool-Aid. However, by popular demand, there was another class at the University of Victoria that used the book, and the graduate student who worked in that class posted materials on GitHub. She had developed some R examples using the models in the book, and so I have a link to them here in case any of you are Kool-Aid and you would like to see what this would look like in LME. I can try to answer questions about R, but I'm a reader, not a user of that. The primary software that we're going to be looking at is M+. However, to get us started in some of the straightforward models, I have examples that are using these 3 programs here, SAS, SPSS, and Stata. So let me see who I'm talking here. How many of you are primarily, would say, SPSS users? Lots of folks. SAS? Hey! Up top. Stata? There's a stated contingent in the back there. Are Kool-Aid drinkers? Yeah, a few people. Okay, yes. M+ users. Okay, a lot of folks. So it looks like I'll be emphasizing for the univariate models probably mostly SPSS and Stata, and then we'll get to M+, and I'll be going over a lot of code in there. So if you haven't seen M+ before, you will get to know it quite well by the end of the week. Let's see. I think that's all the logistical stuff. I have, other readings here that I would recommend. Any questions before we dive in? All right. The packet that you have in front of you is put together slightly differently than I had anticipated, but it still has everything in it. So starting with the syllabus, that has the lecture slides that we'll be doing this morning, as well as the lecture slides for the afternoon. At the end of the other packet, so there's more slides at the front of the second packet here. It starts with lecture 3. At the end of that packet are the examples. So starting on, at the end of the slides, there's pages that start to look like this. These are the examples that we'll be doing first. So we'll do lecture and then example that illustrates the concepts in the lecture, and that shows up where the software is. So I will point that out when relevant, but we're starting off with lecture 1, which is intended to be an overview covering basically the high points of chapters 1 through 7 of the book, so that we can make sure that we're all using the same terminology. So we will start there. Are you ready? We're here, right? We're caffeinated, maybe too much so. It's not on again? Uh-oh. Okay, well, maybe I just need to move it up. Is that better? Is that better? Well, no? Yes? That's better. Okay, thank you for answering. That wasn't intended to be rhetorical. Yeah, if it starts to slip, please let me know. Otherwise, I might just have to have everybody move up. That's the non-technical approach to the problem. All right, away we go. So words. One of the difficulties in longitudinal models are the many, many synonyms that can be introduced in describing things. So I, in theory, would love you to learn all of them so that you can converse about these models in whatever dialect you need to. But I use my own set of words, and so I want to make sure that you know what I mean when I say certain words. So that's where I want to start here. So in longitudinal data, there are 2 primary levels of analysis at which you would direct research questions and have hypotheses. Between person is synonymous with inter-individual differences or time-invariant information. So to the extent that all longitudinal studies start as a cross-sectional study, all longitudinal studies have this. In multi-level modeling terminology of time nested within persons, between person would be level 2 differences, or what is known as the macro level sometimes in multi-level modeling. The extra part, the part that only longitudinal studies give you then, is the within person, known as intra-individual differences, time-varying, level 1, longitudinal, micro. So all of those things mean the same. Another term that gets thrown into the mix is panel, right? That's more of a sociological term. Panel is longitudinal, right? In the way that we're using it? Okay, so panel sometimes means something different, it seems like, but that's basically when you have a unit that is measured over time. And so even though most of my stuff is focused on within and between person, any kind of longitudinal study would have a within and between. So, for instance, educational researchers might be looking at school characteristics that change over time, where they would be looking at within and between schools. Or in political science, people might talk about country characteristics, and they'd have between and within country. Sometimes in animal models, we would have between and within rat, for instance, rather than person. Any animal modelers here? Yeah, you? Between and within rats? Mice. Okay, there you go. So that's your between and within. The words between and within always hold. What they're the between and within of is context specific. So any other between and withins that I haven't hit in your worlds? No? People? I mean, how many people? Mostly people? Yeah? Okay. We'll go with people then. Nice for you. So another way of characterizing different kinds of longitudinal data then is, what was the purpose of making the data design longitudinal? And I have a continuum here that represent the extremes. There's also a lot of possibilities in the middle. But on the left-hand side here is what I would refer to as within-person change, where the goal of the study is to sample occasions that are far enough apart that you would see change over time. So you're meaningfully sampling time. And the type of analysis that people would do for this is what's known as growth curve models, where you can sometimes throw in the word latent if you want to sound fancy. A latent growth curve model makes you more employable than just a regular flavor growth curve model. That just means that you used SEM software to me. But the picture of this on the left here indicates this type of study, where you expect some kind of change on average, and you would also expect people to differ in the extent to which they change. On the other side of the continuum then is what I would call a fluctuation study. And so these go by other types of designs, ecological momentary assessment, that's a mouthful. What used to be called Palm Pilot studies, but now I'm dating myself, which are now, I guess, smartphone studies, the kinds of things where you're sampling people lots and lots of times. What time it is not as relevant as what they're doing at the time. So time is just a way to get a lot of information for people. And, yeah, sure.
So that feels like it's getting towards maybe more towards time series analysis, multiple observations?
Yes. Time series, sort of old school time series, would have very few separate units, each of which is measured for a lot of time. You can certainly combine the two, where you have a lot of people and you have a lot of units, and that's where you get into like people who would do dynamic, time series and that kind of stuff. But yeah, time series would be another way to think about this, although the question is just how much data you would have then at each level. But yes, another synonym for you. Very good. But yeah, so the big difference here is what the role of time is. So in this picture, for instance, time is on the x-axis. Time doesn't really matter. There's no point in these types of models of putting in an effective time per se, thinking that you might have some kind of linear or nonlinear change. You're not making people, say, more stressed out as the study goes on or grumpier as the study goes on, whereas time plays an important role in this side. Now, that being said, in these sorts of studies, there may be time effects that you would have to address that you wouldn't necessarily expect. So, for instance, any of you seen the movie Office Space? Further dating myself? Yes, thank you. Yeah, there's a classic line in there where it says, someone has a case of the Mondays, right? If you collect variables like negative mood or affect or stress or fatigue, your sample may have a case of the Mondays. So to the extent that you want to be able to predict negative mood or stress or fatigue, you would have to address differences due to day of the week before you would be able to do that cleanly. Likewise, things like cortisol have particular biological rhythms where you would have to pay attention to what time of day it is relative to when the person got up, what they ate, and that kind of stuff. So time is just as relevant for within-person fluctuation as it is for change, but in a very different kind of way. Time is something in these cases usually to be sort of controlled for and set aside, whereas time is the point over here. But the same mechanism to put the effects of time in the model in terms of fixed effects and random effects can work for both of these cases. So the examples that I have for you are using both types of data, looking at this morning's example is for change, this afternoon's example is for fluctuation, and then the examples for tomorrow are going to be a hybrid of actually both at the same time. So any questions or thoughts on that? Okay, all right. Other things to think about in characterizing longitudinal data, and more ways that time can play different roles. So first off is, what should time be? And this is something that I've written a lot about because I find it so interesting. In a lot of studies, this is not a question to be answered. Well, I know what time is. It's how long they've been in the study. But in other types of designs, what time should be is actually an open question. So think about sampling, say, grade school children. You might have a sample of 3rd, 4th, and 5th graders, and you measure them over grades. If your outcome is something related to academic achievement or some sort of skill that they've been learning in school, what grade they're in is the logical thing you would keep track of in terms of time. If it's something more biological in origin or something that has to do with developmental trajectories, not academic ones, then how old they are might be more relevant than what grade they're in. In thinking about, say, the tenure process, this is a classic example. You get 6 years to prove yourself worthy, right? Or bye-bye. And when I went up for tenure at Nebraska, there were 4 of us going up at the same time that highlighted this issue quite dramatically. One person had come to a faculty job straight out of grad school. 2 of us had had 2 or 3-year postdocs in the middle, and 1 person had a postdoc and a 5-year K award and then started a faculty job. So as you might imagine, our profiles looked quite different. And the question was, like, what is the reasonable expectation for progress towards tenure? Is it when you walk in the door at your new faculty job? Does the clock start over basically and everything you've done up to that point not matter? Is it only what you've done in the 6 years? Or do we have a different set of expectations based on how long you've been in the field, not just in this job? So where do you start counting from is the issue in those types of designs. And the same thing can happen if you're characterizing longitudinal change along a continuum that started before you got there. So if you're watching something like disease progression, or if you're looking at treatment effects of a new drug, you might want to know how long it's been since the person was diagnosed with whatever they're dealing with, not just how long it's been since they've been in your study. So these are the sorts of questions that you have to wrestle with in certain kinds of designs. And I just want to point out that when I say time, I'm being agnostic as to what the process is. But whatever the theoretical process is that generated the change, that's what time should logically be. Another thing to think about then is whether or not time is both between persons and within persons. So that example that I gave you of 3rd, 4th, and 5th graders being measured across grades, that is what's known as an accelerated longitudinal design or a cohort sequential design. And that's an instance in which time has both between person and within person variation. 3rd, 4th, and 5th graders differ from each other at the beginning of the study. That's cross-sectional between person variation. And you're introducing longitudinal within person variation by measuring them over time. That's 2 different things. So your model has to be able to differentiate effects of cross-sectional differences from effects of longitudinal change. They may or may not map onto each other. And if there's more than one kind of time, then the model needs to be able to account for that too. So I have a colleague actually who collected data when he was a beginning faculty member here, Chris Cushing, where he does multiple times per day over multiple days. So he had 4 occasions per day for 20 days. Well, in that case, he has 2 different types of within-person time. He has within-day changes or fluctuations, and he has between-day changes or fluctuations all within persons. So in that case, that would actually form a 3-level model where within-person is 2 different levels, within-day, between person at level 3. So figuring out what time is usually the first step to figuring out what your model is going to look like and what all it needs to incorporate. And then last but not least here, balance. So to me, balanced, when I use that word, it means people have a shared measurement schedule, not necessarily equal interval. So if everybody showed up at time 0, time 1, time 2, and then 5 units of time later, that's balanced because everybody has the same schedule. Unbalanced means people came whenever. Or they ended up, you were supposed to have balance, but they came whenever, right? People don't always cooperate. They might show up early, they might show up late. So if somebody shows up at time 2.5, do you call that 3 or 2? The answer is you don't. You don't want to round time into convenient bins. You don't have to do that, and it's better if you don't. But that just means that certain modeling options are going to be off the table or are going to be more challenging to incorporate if you have unbalanced time. A different issue is incomplete data. So by definition, unbalanced data is incomplete. Balanced data can also be complete or incomplete. The extent to which you can incorporate incomplete cases depends on what kind of estimator you're using and what you're willing to say about it. And so we'll talk a lot about those options later on. So questions or thoughts on any of this? Okay. Then in more statistical terms here, how I talk about what goes into longitudinal models. All models, longitudinal or otherwise, can be characterized by two different sides, model for the means and model for the variance. So when I say model for the means, I'm talking about fixed effects and what you're used to thinking about in terms of building a model. Yes, ma'am? Okay. Well, thank you for saying something. Maybe I just hold it. Is that better? Yeah. Okay, well, I'll just hold it. It's like I'm on stage or something then. Although I'm getting to sit down, that's exciting. Yeah, thank you for saying something. And then I don't have to yell as much. So yes, model for the means, fixed effects. So when you think about building a model, chances are this is what you're thinking about. The idea of which predictors go in. Do they have main effects? Do they have interaction effects? Is a linear effect sufficient, or is there potential nonlinear effects? This is the part that you probably designed the study around, what data you collected in order to answer your research questions. And I say fixed effects specifically because there's an alternative version of random effects. So when you learned regression, you learned the idea of an intercept and slopes for predictor variables, right? Those slopes and intercepts are fixed effects. You never had to use the word fixed because there wasn't any other kind. But now we have to differentiate fixed from other kinds. What fixed means is that everybody gets the same. When you build a regression model, everybody gets the same fixed intercept or constant. Everybody gets the same effect of X, the same effect of Z, the same whatever. All of those things are constant for the people. And they're all a function of known predictors. The other side of the model is the side that, at least in the classes at KU for your first year sequence, you were taught to make assumptions about instead of choices. And this is the idea of residuals, or the error part of the model, or what we're going to call random effects. If you want to sound fancy, you can call this the stochastic part of the model. That just means error too. But this is the idea of how residuals are distributed and related, and this is the big deal. This is the primary way that longitudinal models or any multi-level modeling framework has to differ from regression. So when you learned regression, right, there's always a little letter at the end of your regression model. What letter was that for you? E, yeah. Any R's? R's for residual, right, or E's? Who put that there? No, I'm serious, like, Fisher did, yes. Well, when you fit your model in any software, you get to pick what goes in, right? You pick what your outcome is, you pick your predictors, you pick whatever form you want them to take. But E or R was just there. And you were told that E or R had to be three things or else, right? What are those three things? Do you remember? Independent, that's the big one. What else? Normally distributed. One more. Yeah. That one. Homoscedastic. Yes, not heteroscedastic, otherwise known as constant variance. Yeah. So the residuals are supposed to be independent, meaning uncorrelated. They're supposed to have a normal distribution, so that's normal residual, by the way, not normal Y. That's a common misconception. Your outcomes do not need to be normal. Only the residuals do, and only if you choose models in which you're saying that they're supposed to be normal. And constant variance. Well, it turns out you aren't stuck with those choices. You are not stuck with those assumptions. If any of those don't hold, you pick a new model. So, for instance, normal. Certain kinds of outcomes are never going to have normal residuals, like binary outcomes. Never going to happen. Count outcomes, unlikely to happen. Categorical outcomes, not going to happen. You pick a new model, and it turns out that there's different models for different kinds of data like that. That's the world of generalized models, and something that I'm hoping we'll get to as our last example in this unit. You can fit longitudinal models on any kinds of data. So there are longitudinal versions of, say, logistic regression or count regression or those kinds of things. In terms of constant variance, that's actually part of what random effects are for. Random effects allow non-constant variance as a function of a predictor. And so we'll see that in our first example. And the big one, dependency. So if you have multiple observations from the same person, they're going to be related. The question is, how do you tell the model that and make a better assumption than unrelated? And how are they related? And so figuring out how your residuals are related across time, across persons, that's where the action is. The model for the variance is the big one. And this is the one that we get lots of choices about. So dependency. It sounds like an ugly word when you phrase it that way, right? Like it's a problem to be solved. But dependency just means correlation, folks. It just means that occasions from the same person are more related than occasions from different people. And that can be for more than one reason, and that's where the tricky part comes in. But there are three main approaches to allowing residuals to be dependent, meaning allowing them to have a correlation that they actually have in their data. One of those is fixed effects, and this is common still in certain areas of econometrics and sometimes in sociology journals. I see this, the idea that you can control for all of the dependency introduced by person by literally controlling for person. So if I had a study of 50 people, I would put in 49 dummy codes tied to their ID variable, and those dummy codes entered as main effects would account for all mean differences across people. If I wanted to also control for slope differences, say in an effective time, I would have 49 dummy code by time interactions. And then I have totally controlled for all between-person sources of dependency in intercept and time slope. Now, if you don't care about your people at all, that's a perfectly fine approach. But most of the time, people care about your people. So the downside of that approach is that you can't then put predictors in because you have already explained all the reasons that people are different from each other with their ID variable. So it's not an explanation so much as a control. It's unsatisfying from the perspective of testing between-person relationships. Then there's the sort of the intermediate version that sometimes gets taught in the context of repeated measures ANOVA, the idea of just changing the error structure into something that has a correlation to it. So a classic difference then, different kinds of ANOVA, right? ANOVA folks in the house? Am I speaking your language? Yeah, a couple people? Really? That's it? No one wants to admit having been taught ANOVA before? Yeah, it's not a dirty word. There's nothing wrong with ANOVA when it fits. The problem is when people shove data into an ANOVA that weren't meant for an ANOVA. That's where the problem comes in. But between groups ANOVA, right, that model says that the residuals are uncorrelated across people and across time. So we switch to a repeated measures ANOVA that allows a constant correlation. The idea that you're holding each person as a control and you kick that variance out of the denominator of your F-test so that you get a stronger test of your repeated measures factors. Well, the thing that got kicked out of the F-test, that's actually at random intercept variance. And so that introduces a dependency of a particular kind, a constant dependency. It says the only reason that the residuals from the same person were related is because of constant mean differences, and that is it. In other words, it predicts parallel change. No differences in effects of time or anything else. And so for that reason, it can be unrealistic. There are other variants, though, of those kinds of structures. There's an alternative, for instance, compound symmetry heterogeneous, which says that there's still a constant correlation over time, but your variances get to differ over time. Or the multivariate approach to repeated measures ANOVA, which is the unstructured model, as I talk about being the answer key, because in that model, all your variances and covariances over time get to be whatever they want. So then there's these other options, too, that you can use for longitudinal data that are all predicated on an idea of a time lag, introducing certain kinds of correlation. But all of these things just take what was some kind of dependency, and they try to mimic it by a predetermined pattern. And so they estimate parameters that define these patterns, and there's your dependency. The third option is the one that I think is potentially more interesting and useful and also amenable to unbalanced longitudinal data. So another problem with these ones is that you have to have balanced data to use them. So this is the idea of turning it from a single level model, going from a single level multivariate into a multi-level. And so when we say add a level, what we're actually talking about is adding a set of random effects for person, otherwise known as latent variables. And so this is where we get to the intersection of longitudinal modeling, thinking about it as a multi-level model versus a structural equation model. Random effects are latent variables. So you can think about it from either perspective. But their job, what the job of the latent variables and the job of the random effects is to introduce kinds of dependency, to be able to put the dependency in the model so that we no longer make assumptions that can't possibly be true. And so that's what we're going to spend our time on, is this type of strategy. So before I dive into that, questions or thoughts on any of that? So, please. An AR1 structure all by itself doesn't need a latent variable. You could, if you wanted to fit an AR1 structure, you could do that without invoking random effects or latent variables. Is that what you're asking? Okay, so yeah, so these models often get stuck in as a chapter in longitudinal books. Singer and Willett has a chapter on them. They show up in some of the others. They show up in mine in chapter 4. You're making the assumption that that is the correlation pattern in your data. So if you fit what's known as unstructured, or what's known as the saturated model in SEM parlance, that's the idea that if you have we're going to see some matrices in just a second, but I'll sort of draw on here. Like if you have the variance at time 1, the variance at time 2, the variance at time 3, and all the covariances between them, when you fit unstructured, you're saying that each variance gets to be whatever it wants, and all pairs of covariances get to be whatever they want. When you fit an AR1 then, for instance, you are saying that that AR1 pattern can mimic what's in the unstructured, what's in the real data. And in the data that I've seen, I have never once seen AR1 fit. Never once. I have a lecture about this that I give where I make an analogy between these types of models and different styles of genes. And no, seriously, because unstructured is sweatpants. It's always going to fit, or what is known as athleisure nowadays. Whereas compound symmetry is like skinny jeans. Like, they fit some people, but they're not meant for everyone. And so AR1, I always say, is tapered jeans, like back from the 80s where they had the tiny little, like, things at the bottom. And any of you who used to watch What Not to Wear with me would recall that Stacy and Clinton hate tapered jeans because they narrow too much, and it's the same problem with AR1. That's why I call them the tapered jeans, is because it says that the correlation between occasions 1 unit apart are R, 2 units apart is R squared, 3 units apart is R cubed, and so on. It makes the correlation die off really, really quickly, and in longitudinal data, that just doesn't happen. What works out much better with that is a random intercept variance plus an AR1, where you have a constant correlation over time due to the random intercept, and then you can add an AR1 on just the residuals. But whenever you fit these structures, you are saying that's the pattern that's in my data. And when you have unbalanced data, you won't ever get to fit the answer key. But if you have balanced data, then that's a likelihood ratio test as to whether or not that pattern is actually not worse than what the original data say. Long answer to a short question. Did that help? Okay. All right. Other questions? Yes. All I heard was moving average, and I missed the rest. I'm sorry. Moving average on the variance? The moving average model, I think, can be somewhat equivalent to AR1, but with heterogeneous variances, right? The ARMA one. But it works the same way in that it's just saying, well, here's what the pattern of correlation looks like. I'm going to try and make a pattern out of it so that I can estimate fewer parameters to capture it. But it's not saying anything about why the pattern is the way it is or trying to make levels of analysis out of it. It's like taking all of the information, keeping it in one place, and it's not trying to pattern by making a distinction between and within. It's just all total, and it holds that pattern. But yeah, the ARMA models is another type of pattern that you can fit in a lot of software. Is that what you wanted to know, or I'm sorry, I'm having a hard time hearing you. Okay, fair enough. All right. Others. So yeah, if any of you have only 2 occasions, I'm here to tell you that I cannot help you. I cannot make 2 occasion data any better. There are lots of things you can do with 2 occasions, but adding random effects is not one of them. You can have a random intercept, but you can't have any random slopes. So for 2 occasion data, I tend to approach it this way, just letting pre and post have different variances and some kind of covariance, fitting it as unstructured and calling it good. So I think of that as single-level multivariate rather than multi-level because you can't have more than one kind of random effect for 2 occasion data. So this last level here, is predicated on having at least 3 occasions per person to be eligible. All right. Yeah. Hypothetically, tell me about an example in which that would happen. So the extent to which you can have a predictor measured twice and an occasion measured 3 times depends exactly on how you put the predictor in. What do you expect would happen with inflammation? Decrease. Okay. So then with 2 occasions, you won't be able to differentiate the extent to which it decreases differently across people from residual error, because if you give each person their own line, that line's going to fit perfectly. What you could do potentially is put in a predictor for their initial level and then another predictor for their change in inflammation, and think of those as time invariant because they're characterizing the person, and then you could have each of those predict the 3 occasions as time invariant predictors. So it'll be 6 of one, half dozen of the other as to what you put in. You can either have their occasion 1 and occasion 2, or you could have occasion 1 and the change to 2, or you could have 2 and the change back to 1. 2 out of the 3 will get you the 3rd. But I'd probably approach it that way rather than thinking about it as a time varying predictor, because if somebody is going to decrease in inflammation, they may have looked different in terms of their weight from the get-go. So I think it does make sense to predict, even if they're not, to predict backwards in time if you think of it as like foreshadowing. So does that help? Okay, cool. Yes? That's exactly what I just suggested, yeah. I would have like the initial covariate at is it the first occasion? Which one are you skipping? Okay, so you have it at 1 and 3, but not at 2. So yeah, so that's what I would do is, in that case, I would put in the time 1 predictor as a level 2 time invariant predictor, its change from 1 to 3 as a level 2 time invariant predictor. And reviewer 3 is going to yell at you, of course, because you're not differentiating. You can call it a change score. I mean, it's a different score, but it's both residual and individual differences in change commingled because it's not identified to separate the 2. but that's an area for future research. You just stick that sentence in your limitations to just head it off from the get-go. But yeah, that's what you would have to do, I think, in that case. Yes, sir. Yep. 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 If you have two waves, you can have either a random intercept and a random slope, meaning that each person gets their own starting point and their own rate of change, or you can have a random intercept and an error term. So whether you call it error term or random slope is a semantic distinction. And actually the models that, like the latent difference score or latent change score models that have two occasions and they somehow use SEM to try and trick it, nope. They have to shut off the error term to make that work too. So when you only have two occasions, you have one difference between the two of them, and that is both change and error. You just have to be careful interpreting it. Yep. Others? All right. So then more vocabulary. How do we approach this? So longitudinal models, or any models really, are logically separate from software. So I can talk about the models and what's in them in terms of their parameters, how to think about the linkage between models and data and questions, but ultimately we're going to have to also think about software to be able to estimate them to get the answers back. And so that's where the tricky part comes in, is how do I do this? And I want in this workshop to tie together the different ways that people approach this so that you can see how they are the same, and when they're not the same, how they differ, to be able to use this as a set of alternatives, because ultimately it comes down to what can the software do and which way to do it is the least painful. Those are the two considerations. So when I teach longitudinal modeling, I start from what is known as the multi-level framework, and I have all of the synonyms here. So what I call a multi-level model, I like that term the best because I think it's the most general and descriptive, is also known as a mixed effects model. So if you have a general linear mixed model in statistics, that's the same thing as this. If you take the same class in education, these might be called hierarchical linear models, or HLMs instead of MLMs, not to be confused with hierarchical regression, which is a stepwise thing that's different. But because these models are expressed looking like regression models, because their parameters are interpreted similar to regression models, this is where I start. I think this is the easiest place to start from because everyone in my class would have had regression in ANOVA as a starting point. And in this framework, the way that we capture dependency, the way that we capture the correlation of occasions from the same person is through random effects. And a level of the model is a set of random effects. So if I have in a straightforward longitudinal design with just one kind of time, so like 3 occasions within a person, then I have one level that is time, and I have a second level that is person. And each of those has its own set of error terms. Random effects are what the error terms are called at level 2. And by introducing additional levels, I'm introducing these different kinds of dependency. And I do so in a data structure in which one row is an occasion within a person. And software for univariate MLM then has one outcome over time that we're estimating these random effects for. And this is common. I'll show you how to do this in SAS, SPSS, and Stata in their mixed package. It's good for small samples in that there's an option for estimation that's known as residual maximum likelihood that gives better results in smaller samples. It also has options for denominator degrees of freedom, which start to matter in small samples. And this is usually the most straightforward way to jump from a single level model into the world of multi-level models, but unfortunately we can't stop there because certain types of hypotheses can't be tested using this univariate approach. So SPSS mixed, SAS mixed, Stata mixed, all of those are a great place to start, but they're not a great place to end. Transitioning then from what we call univariate to multivariate is when you have more than one variable measured over time and you're trying to estimate variances at each level for both variables simultaneously. So if you want to test something like within-person mediation, or you have any kind of hypothesis in which the random effects of one variable predict the random effects of another, that's where you're into this world of multivariate MLMs. And the only software that I know of that has this option is M+. I keep asking, does anybody know how to do this otherwise? And I haven't heard yet. So the M+ between within version is what we're going to look at for this, and this is the option that you need in order to treat more than one variable as an outcome simultaneously and have the random effects predict the other set of random effects. The downside is that that software only comes in maximum likelihood flavor. There's no residual maximum likelihood. There's no denominator degrees of freedom. And so this approach is not as good for smaller samples of persons, and it also requires more parameters, which means it's more likely to throw up in smaller samples as well. And what I call multivariate MLM is sometimes called multi-level SEM. I don't like that term because there's no latent variable measurement model in place, and so to me it's not SEM. The other way that longitudinal analysis is taught is through the logic and language of structural equation models, or SEM, in which case you have a different data structure. Each occasion is a separate variable in what's known as a wide or a flat file, so it's one row per person. And dependency is captured by latent variables instead of random effects, but it's 6 to 1, half a dozen of the other. So you might have a latent variable that defines intercept differences, another latent variable that defines time slope differences, and so on. SEM software is very common. It also suffers from the same limitations in terms of estimation. There's no version of REML in SEM, for instance, and no denominator degrees of freedom, and so these models are not as well equipped. The software is not as well equipped for small samples. And last but not least, then, is this idea of the change in the data structure and what that implies about your measurement of time. The fact that you have a separate occasion as a separate variable implies that you have balanced data. You have a box for time 1. You have another box for time 2, and so on. But if you have time 2.5, which box does that go into? So you have to be able to tell the software that time 2.5 is legit to have. And in M+, there's an option to do that via T-scores. I don't know if in other SEM packages if the same option exists, but that's something that you would have to look for if you have unbalanced time. So in your study, for instance, is everybody coming at exactly the same time at time 1? Uh-huh. Okay, so she's using air quotes. That's never a good sign. It's baseline. It is. So is a 4-week window wide enough to see change in the things that you care about? Mm-hmm. But the extent to which, if you're measuring it, week 1 or week 4, like that's extra noise potentially that, yeah, it's an empirical question, I think, whether or not you would think of your data as balanced or not. But for cases where it's like it's all over the place, like people really just came whenever, this is a serious restriction to using these sorts of models. You have to be able to tell it when exactly the times were, and if it's not balanced, then you may not be able to fit it as an SEM. Yes, sir. T-scores is one fix, but it's not a fix for everything. Yeah.
But it does allow for flexibility.
Yes, and that's the only instance in which I've seen that used. I've also seen the exact same model not converge using T-scores, and then I ran it on the MLM side, and it converged like that. So there is T-scores, yeah, and we have an example that uses that. Yes, sir. I like teaching starting with the multi-level approach. I like those systems of equations for presenting the model. The problem is when you get stuck in a univariate framework. And so I like ideally to start there in terms of introducing the ideas and the terminology and then making sure that people take those same information into the world of SEM. Because comes a point at which SEM doesn't do it right sometimes. And so that's what I have a couple examples in here of what not to do with SEM. And I feel like it's more prone to not being right at the first step. So it's not that I necessarily have a preference. The world that I live in, a large sample is like 30 people. Like we have special populations that are hard to find. And so the idea that I'm stuck with maximum likelihood instead of REML is often discouraging. So I want you guys to be able to understand how these things intersect and to be able to figure out how to get what you want out of the software. That's the objective. So unfortunately, I have to spend more time talking about software than what I would like, but that's the reality of the world we live in. Other questions or thoughts? All right. So other terms then that these models often go by in terms that you can ask the Google for help if it's important to have the right search terms. So from a statistical point of view, the models that we're talking about fall into this box here, where we have multiple dimensions of sampling, and that requires the existence of both fixed and random effects. So when we have a terminology here, general versus generalized, general means normal residuals, and generalized means some kind of not normal residuals. So the idea that you have a Bernoulli distribution or multinomial or Poisson or something like that instead, that's ized. That picks up that part. The next word in here, linear, shows up in all of these because what linear means is that the predictors are put together in a linear fashion of slope times variable plus slope times variable plus slope times variable. So even if you have, say, a quadratic time term that predicts nonlinear change, the way that it enters the model is in this linear additive fashion. Then we get the mixed versus just no adjective here, and that's fixed and random effects. And so mixed then means the combination of both of these. And so these models then we're starting with are general linear mixed models because all of the residuals are supposed to be normal, meaning that we're using a multivariate normal distribution to do the likelihood. But if that's not tenable, then we'll switch to generalized. And the last example that I have for you works with some of those models instead. So more terminology for you. All right. Yeah.
Would you agree that if you're going to talk to a social science person, you're going to talk about multi-level HLM, but if you do go to a statistician, like a department of statistics, they're going to look at you funny when you say mixed?
Yes. Yes, that's exactly right. It really is, I don't want to say marketing because that sounds crash, but knowing your audience and knowing the words that will make sense to them. Absolutely. So if you want to hedge your bets, you can say multi-level, parentheses, i.e. everything else, right? HLM, general linear mixed models. But yeah, if you go to a statistics department, you need to say these words. You need to say general linear mixed models and for them to nod their heads. I'm not trying to be overly simplistic, but yeah, that's the predominant way these things are described, and that's the names of the textbooks in here. Absolutely. So yes, we are in the world of multi-level / hierarchical linear models / general linear mixed models. And you can fit those as using multi-level modeling software or using structural equations software. There. All right. Other thoughts? Okay, so then that's the end of the terminology section here. The rest of this then is reviewing big picture concepts that are going to show up then in terms of transitioning from general linear models here up to mixed models. Oh, thank you. Red things are fixed, blue things are random. And so yes, so starting from a single level model then and building our way up into something that would be more appropriate for longitudinal data. So for example here's a regression model. I want to point out the subscripts because subscripts are really important when you're writing out equations for these. And by the way, whether or not you need an equation in your paper depends on where you're submitting as well. I've often had painstakingly made my equation nice and perfect, only be told to shove that in an appendix because we don't care. But for Reviewer 3 to know exactly what you did, it can be helpful to have an equation, whether it's in an appendix or the paper, it depends on the journal. So in my notation here, this is what I call a single level model. So this would be appropriate when you have one occasion per person, cross-sectional study. So Y sub I means each person has their own Y, in I for individual here, and because there's one Y per person, there's one E per person. In the red here, this is the model for the means. So note that X gets an I and Z gets an I because each person has their own value of those, but beta 0 doesn't have an I, beta 1 doesn't have an I. These are fixed effects. The betas are fixed. Everybody gets the same fixed intercept. Everybody gets the same slope for X. And so this is where the term model for the means comes from, the idea that if somebody has the same X and Z, everybody with the same X and Z is going to get the same predicted Y. So it's the predicted mean for that person, but it's made conditional by the predictors in the model. So it's a conditional mean, but it's still a mean in the sense that it's for everybody with the same X and Z values. The model for the variance then is this little thing right here. One letter, one pile, one term. So we would say that the E's are supposed to have a mean of 0 because their mean is over here in the red part given by the fixed effects. They have a variance that the model finds. And the thing that we concentrate on is not what the E is for each person, but their variability across people. And that's important because what that means is that E is representing one parameter, not many. It represents the idea that we have a residual variance. And so then moving from this model to something longitudinal, we have to start with a simpler version, empty means. So empty models, also known as unconditional models, unconditional means rather, that means there are no predictors. You would never do this in regression, but this is always the first step in longitudinal data. If you know nothing else about a person, what's your best guess for their outcome, folks? The mean, yeah. So that's this, right? That's beta 0. So in this case, this is not a good guess for this person down here, but this is my best guess from an empty model. And the variance then is all the variance. Just having a mean in the model is the definition of variance. That's how one computes variance. So E at this point represents all the variance there is to be had in Y. So if we transition from cross-sectional data to longitudinal data then, this would be an example of, say, a fluctuation study where the heavy black line is the sample means. There's no change on average, but people are sort of bopping up and down here. An empty model would look at the difference between the outcome mean at each occasion and the actual value at each occasion and say that's all error. So for this purple person here, this is their error term on the first occasion, this is their error term on the second, and this is the third. But this doesn't work because these E's are supposed to be independent, right? Do you see any kind of dependency here? No, they can't all be negative, right? Some of them have to be positive. So this doesn't work. So how do we fix it then? Well, if we have 5 occasions per 3 different people here coming out of this pile here, I've got a blue person, a yellow person, and a purple person. Rather than guessing the same sample mean for everyone, I take advantage of the fact that I know from which person each observation came. So a better guess than the sample mean would be their own mean as a starting point. So I'm going to take each person and give them their own mean, and then I'm going to indicate how far off from the sample mean their own mean is by another letter. This is going to be our friend U. U represents between person differences, and we get a 0 because this is an intercept, and an I because each person gets their own. So this idea of why doesn't everybody get the same mean, that forms what is going to be known as the level 2 random intercept variance. So it's the variance of the U0s across people. Following other folks' notation, I indicate that with a tau squared, but I always say what it is the variance of as the subscript here. So this is between person variance, this is cross-sectional variance, this is the variance that would have been there had you only measured them once. People differ from each other. The idea that it's on average is because we have longitudinal data with which to anchor each person. From there, once we give each person their own mean, E is what's left. It's the difference between the person's mean and their observation at each occasion. And so this is going to be what's known as level 1 residual variance, or what is within person intra-individual variation. So to show that then on the same picture here, my purple person, for whatever reason, is below the mean all the time. This picture then shows that is their source of dependency, so let's fix it. U0 for the purple person is the difference between the grand mean and their mean across time. From there, E is the remaining difference between their mean and that specific occasion. So we have taken what was one kind of variability and carved it up into two. How much of it is level 2 differences between the person means, that's the U0 intercept variance, and then how much of it is level 1 within person variation around your mean. So carving up these sources of variance into two piles allows a source of dependency then, a source of correlation, due to U. But it's the only source of dependency. The only reason the E's from the same person were related is because of constant mean differences, is because of random intercept, is because of this, and that's it. So putting it together then looks like this in equation form. Yes, sir?
So in this process, the U and the E are now follow those three assumptions we needed before.
Exactly. So by splitting it up, the E's are now normal, independent, and are supposed to have constant variance. The only reason that they were dependent is moved over here, is the U0. And to that end, the U's are also normal, independent, and have constant variance. So that foreshadows then what might happen to the model if they're not. So can you think of a case in which the U's would be related? What about people from the same family? People from the same school? People from the same hospital, et cetera, et cetera? Well, then this model doesn't work for that kind of data. What would end up happening is this U0 right here would have to get split into a third pile. That would allow a correlation between people from the same unit, in addition. But that's the logic. We start with everything in one pile, and we keep splitting it. We keep pulling piles out of it until each pile then meets the original assumptions that you were told you had to have: independence, normality, and constant variance. Yes?
Sometimes, maybe all the time, it's part of the fun of figuring out what the data is telling us, figuring out stuff like that. Like, for me, maybe it's, instead of being grouped by, we just say from what hospital or from what big kid.
Yeah, people within groups.
Part of it trying to figure out, like, maybe it's from what region of the state, or maybe what, like that.
Yeah, so you might have more than one hypothesis for how people might be related to each other. They can all be phrased as testable models. To the extent that you add a term that splits this U0 variance into two different variances and it makes your model fit better, then you're right.
So you might run it like that and then say, hey, I wonder what would happen, like maybe it has something to do with this, and then you run it like that.
Yeah, it presupposes that you have an idea as to why people are related. You have that variable in your data set with which to test that idea. All right. So then setting up that same idea using multi-level modeling equations. This is what's known as an empty means random intercept model. empty means meaning no predictors. This is always step one. Always, always, always in longitudinal data. This is rarely sufficient, never sufficient, but it is a useful descriptive model just to see how much variance you have of each kind. So previously we had an empty model that looked like this from a single level perspective. We are swapping out several key terms here. So now my y is ti for each time for each individual. Because y is ti, e is ti. And beta 0 picks up an I. Beta 0 is no longer a thing. It is not an estimated parameter. It is a placeholder. Let me get my, where is my pointer? There's a laser pointer. There we go. It is a placeholder that gets defined at level 2. So beta 0I is how each person gets their own intercept. And it comes from two places, the fixed and the random. Fixed is the part that everybody gets. And so this Y-looking thing here, I'm using gamma to notate this. In different fonts, it sometimes looks like Y, sometimes looks like V. But this fixed intercept is the mean of the person means. Now, I say that deliberately because of the difference in what you get when moving from a single-level model to a multi-level model in unbalanced data. If you were to just run, proc means or descriptives in your program, and you can figure out what the mean is, right? If your data are unbalanced, if you have a different number of occasions per person, that mean is probably not going to match this one. Because the mean of the means is only the same thing as the sample mean if everybody contributes the same amount of data. So it carries a slightly different interpretation. This is the average person mean. From there, U0 is how far off you are. So these are random intercepts. They are phrased as deviations. So if I'm the purple person who's lower all the time, my U0 is negative. If I'm doing better than everybody else, my U0 is positive. Put these back together is how we get to each person's intercept. The equation that clearly show the three parameters that we're going to estimate. Gamma 0, 0, my fixed intercept. U0, which has a variance we estimate. In the same way that we don't estimate separate e's, we estimate their variance. So this is critical in the sense of model comparisons. Even though this is the idea that each person gets their own U0, we're adding one term, their variance. We don't actually need to know what the U0s are for any person. It's just an idea. In other words, U0 is a latent variable. It's like a factor score. And in fact, if you were to try to ask the software to predict the U0 for each person, it would be a weighted blend of what each person's real mean is and the one that is predicted for them by the model, because anybody who has a mean that's really discrepant would have it pushed to look more like everybody else's data. There's a term for that called shrinkage. And so you don't actually want ever to get these U0s out. You don't need them. We want to leave them in the model to be predicted by other things. So in terms of what is happening to build the pattern of the data, more terminology here. By taking our original pile of variance here and splitting it into two, the u's go someplace else. So where the u variances are going is someplace called the G matrix. This is what it looks like on your output. You'll see a little thing that looks like this. The e's that are left, then, the model says they're supposed to look like this. And so this is for 5 occasions within a person. This structure is what's known as identity, or VC in SAS, or independent in Stata. And it says that the E variance is the same across time with no relationship whatsoever. In other words, the only reason that the E's from the same person were correlated is now over here in G. So adding all the synonyms back together here, G is the level 2 matrix of random effect variances, which represent between person differences. So far, we only have intercept differences between people. Over here is level 1, within persons, longitudinal, E, residual variance. And so this is a strict assumption that all of these E's are supposed to be the same across time, have the same variance across time and no covariance. And this is where you can add things to the model if this is not true. So for instance, you can say that these E's have an autocorrelation. That's a testable hypothesis. You can test that they have different variances across time, but that would require you to have balanced data. So levels are a way of creating patterns that capture person correlation or person dependency. And the name for the pattern put all the way back together again that shows the predicted data is up here, is what's called the V matrix. So I'm not a matrix algebra person. Seeing all of that stuff doesn't help me, but I have it on the next slide. But for those of you who are not matrix algebra people, think of it this way. Take this random intercept variance here, and if you just like stick it everywhere in this matrix, you get that one. Good? For those of you that are like, you can't do that. I know. What ends up happening is there's another matrix that pre and post multiplies this one to get it to be the right size, but it has only ones, and it indicates how many occasions each person has, and so that's how it actually ends up happening. But conceptually, this is important to indicate we've got a level 2 and a level 1, but what the model's really trying to do is use those to create this pattern, the pattern put back together again. The levels are just a device to get there. That pattern then gives us a very important descriptive statistic known as an intraclass correlation. So I have it written here a couple different ways. You can think of it as how much of your variance is between persons over your total, how much of it is due to intercept differences at level 2 relative to total. There's a notation for it. And you can also think of it as the expected correlation occasions from the same person. So if you take that pattern here of the variance at each occasion is partly intercept differences at level 2, partly residual variance at level 1, the off diagonal is random intercept variance right here. So what that's saying is that the only reason for correlation between occasions from the same person is that random intercept, and that's it. So it's the same across time. And when you translate that covariance into a correlation, you get the ICC. So the ICC is the proportion of variance that's between. It is how much of your data is actually cross-sectional. It ranges from 0 to 1. If you have an intraclass correlation near 1, you don't actually have longitudinal data. So that's why we always start here. We can do a hypothesis test to see whether or not this random intercept variance helps the model fit better. This intraclass correlation can be seen as an effect size for that hypothesis test. It's a standardized way of expressing how much of your dependency is due to between-person mean differences, is due to cross-sectional variance that was already there to begin with. All right. So questions on that slide? All right. So then that actually gives us a good place to stop for a break. So let's take 20 minutes or so, and I'll see you back then.